Hello and welcome to the next video. In today's video we will discuss about some other instruments. We'll start with potentiometer. So here is a basic construction of a potentiometer inside the green box. It has a driving battery. It has a rheostat, which is nothing but a resistance which can be varied, and it has a long wire across which a potential drops continuously. So let me assume that or let us assume that across this whole wire from A to B long wire, the total potential drop between across the full wire is V naught. So we know that if across the full wire it is V naught, then across any small portion at say L by 2 or L by 4, the potential drop will be proportional to the length of the wire. So at any point inside the potentiometer, say at a distance L, so let me say that this distance is L and this total distance is L naught. So from here to here the total distance is L naught with a potential difference of V naught. So here across any smaller length, the potential, because the potential drop will be proportional to the length of the wire, so V will be equal to the potential drop across any length L will be given by V naught divided by L naught into L. So now if I want to measure the potential drop across any object in a circuit, say I want to measure the potential drop across this resistor. So what I will do is one end of the resistor I will connect it with the point A. So let me say that this is point O. So point O will be connected to A, and the other side is connected through the potentiometer by a jockey through a galvanometer. Now what I will do is, suppose the potential drop across this is V dash. Okay. Now I will take a galvanometer, connect one of the end of the galvanometer to the other side of the resistance, and I will move this jockey to find a point such that there will be no current flowing through this galvanometer. So what basically happens is, suppose the potential difference between the resistance across the resistance is V dash. Okay, when I take this jockey from this point and move it across, so the potential difference is 0 here. Now as I move across this, okay, the moment the potential difference across, say I say it a point A, C, and this point is OD. As I move this jockey around and find a point C such that the potential difference between A and C, okay, now because I have connected O and A, now O and A will be at same potential. Now if O and A are at same potential, now I have to find a point in this wire whose potential will be same as point D. Okay, so as I move this across this jockey across the wire, I will get by trial and error a point in this potentiometer, because at different points the potential will be different depending on the length or the distance from point A. So I will find one point C where the potential at C will be same as potential at D. How will I know that I have found such a point? I will know when this galvanometer shows zero deflection or there is no current flowing through the galvanometer. When there is no current flowing through the galvanometer, that means the potential difference across the galvanometer is same. That means the potential at VD will be potential at D will be same as potential at C. So once I find that length L where the potential at D is same as potential at C, then I will know that what is the potential drop across that resistor by using this formula, by just knowing what is the length which is giving me zero deflection at galvanometer, and using this formula V naught by L naught, the potential difference is equal to, because I've connected battery here, so this potential becomes same as this. The moment I find what is the point which has same potential as VD, I will know that what is the potential drop across this resistor. So this is the basic application of a potentiometer. It helps us to find out what is the potential difference across different point measure the potential difference across different element of the surface of the circuit. So not only across it can find the potential difference across the resistor, I can also use to find what is the EMF or compare the EMF of two batteries. Okay, so instead of this resistor, what if I want to compare the EMF of say two batteries, what I will do, I will put a battery of say EMF E1. Okay, now I will suppose I want to measure the potential difference, compare the EMF of two batteries whose EMFs are E1 and E2. So I will first put E1 here and find what is the length. I will find the length which is giving a zero deflection in the galvanometer. So using this formula again, I will know that the potential difference or the EMF of the battery E1 will be equal to say V naught by L naught into L1, the length where the first EMF I get a zero deflection for galvanometer. Then I will change this battery and put another battery, the second battery E2 here. So I will put E2 here, then find a new length L2 again by shifting the jockey here, which is giving me zero deflection of the galvanometer. And then again using the same formula for potential, I will get E2 is equal to V naught by L naught into say the new length where the galvanometer is giving zero deflection is L2. And if I just divide, say this is equation 1 and this is equation 2, if I just divide E1 by E2, that will be equal to L1 by L2. So just by knowing the different values of L, I can compare the EMF of two batteries which has a higher EMF, or how many times E1 is greater than E2 or less than E2, and so on and so forth. Another application is the measurement of internal resistance of batteries. So internal resistance of the battery, like we all know that nothing is a perfect conductor. Everything has a resistance. So even the batteries have a resistance, which is known as the internal resistance of the battery. Now this can be denoted by putting a battery and in series with it putting a small resistance R to it. So this is the way of notation of how we denote an internal resistance of a battery. We just put another small resistor R beside the battery of EMF E. Now suppose I want to measure what is the internal resistance of a battery. So to do that, I have to use of the setup as shown. Now I take a potentiometer and I also connect a resistor like as shown in the figure with a switch in it. Now first method is I open the switch and then find out what is the length which is giving me zero deflection of the galvanometer. So let that length be L1. Okay, now from the EMF formula we know that when this switch is open, then there is no current flowing through this. So the current flowing through the internal resistance is 0. So because the current flowing through the internal resistance is 0, that means potential drop across this small internal resistance is 0. That means the potential difference between this point and this point with when there is no current flowing through it is just the EMF of this battery. But my first equation will be using this formula. When the switch is open, it is E is equal to V naught by L naught multiplied by L1. Now what I do next is I close this switch. So when I close this switch, the total resistance of this internal circuit will be R plus R. So the total current flowing will be V is from Ohm's law, V is equal to Ri, or here the total potential is E and the total resistance is R plus the capital R. So this is the capital R. So E is equal to R plus R. So what will be the potential difference across, suppose this is VA and this is potential here is at VB. Okay. So the potential difference across this, or between this point and this point, the potential difference between this point and this point is same as the potential difference between this point and this point, because they are connected by a perfect, assuming that they are perfect conducting wire. The potential difference between VA and VB will be same as potential difference between this point and this point when the switch is closed, and which is the potential difference between this point and this point is nothing but V is equal to Ri, which can be deduced by using this formula. So potential difference VA minus VB will be equal to Ri, and R is the resistance of this resistor, and I is the what we have deduced here. So E by R plus R. Now suppose this potential difference with this new potential difference, the point where the galvanometer is now giving zero deflection is suppose at another point, say this point, which is at a distance of L2. Okay. So now if we use this formula, just again the formula for potentiometer, VA minus VB is equal to VA minus VB, which is the potential difference, is equal to V naught by L naught. Now the new point is L2. So if I just substitute this from here, what I will get? I will get RE by R plus R is equal to V naught by L naught into L2. Okay. Now suppose the original equation was this, I write equation 1, this equation I write it equation 2. If I divide this equation by this equation, okay, so this V naught by L naught and V naught by L naught will get cancelled, E and E will get cancelled. Okay, just dividing 1 and 2 and simplifying, what we will get is R by R plus R by R plus R will be equal to L2 by L1. And if I just simplify this for R, I solve this for R, I will get R is equal to capital R L1 minus L2 divided by L1 by L2 divided by L2. So if you just use this formula, this of L2, so the way by which I can measure the internal resistance of a battery is, I take the circuit which is shown here. First I open the switch and find the point L1. I find the point L1 where there is no current flowing through the battery. Then I close this switch and then I find the point L2 when there is no current flowing through this galvanometer, and then uh, using that L1, L2 and knowing what is the value of capital R which I am using, I have to use R whose resistance I know. Then I can calculate the internal resistance of the battery using this formula. Next topic which we will discuss is Wheatstone bridge. We all know what is most of we have studied this in lower classes, but I will quickly go through this again. Wheatstone bridge is a instrument, or the setup can be used to know the resistance of an unknown resistor, say R2. So out of these four resistances, if I don't know one of the resistors, then using the Wheatstone bridge setup, I can know what is the resistance of the unknown resistor. So in a Wheatstone bridge, what happens is we choose those uh, we choose the resistors in such a way that there is no current flowing through this galvanometer. So there is no, so let me denote this point as A, this point as B, okay, this point as A, this point is B, this is C, this is D. So if I have four sets of resistors arranged like this, such that there is no, and everything is closed, if there is no current flowing through this galvanometer, then this type of setup where there is no current flowing through this galvanometer, that is known as Wheatstone bridge. Now if there is no current flowing across this galvanometer, that means the potential at C, Vc, will be equal to the potential at T. That is the condition where there is no current flowing through this galvanometer. Now let us assume that a current I is flowing in the circuit. Of that, I1 is going here and I2, that is being divided into two branches, I1 and I2, and I1 is flowing across this, and because there is no current flowing through this, the current flowing through this resistor is same as the current flowing through this resistor. Okay, so let me from Ohm's law, let me apply Ohm's law to each and every resistors. So Vc, so the potential difference across this resistor is Vc minus Va. So this should be equal to I1 R1, because I1 is the current flowing through it. Similarly, Vc minus Vb will be equal to I2 R2. Okay, now if I divide these two equations, equation 1, equation 1 by equation 2, sorry, this is not I2, this is I1 only, same current as I discussed, because there is no current flowing through this, the same current will flow through R2 as the current which is flowing in R1. So here it will be I1. So this is I1 R1. So VA minus VC minus VA divided by Vc minus Vb will be equal to I1 will get cancelled. So R1 by R2. Similarly, in this resistors, Vd minus Va will be equal to I2 R3, and Vb minus Vd will be equal to I2, same amount of current is flowing here, I2 R4. So if I again divide these two equations, I will get Vd minus Va divided by VB VB minus VB minus VD is equal to R3 by R4. Okay. Sorry, D will be at a higher potential than B, so I have to write VD minus VB. Here it should be VD minus VB, because D current is flowing from here to here, so D is at a higher potential than VB. So here also VD minus VB. Okay, so we have these two equations now, this one and this one. If we assume, not assume, if there is no current flowing through the galvanometer, then VC is equal to VD. Then this VD can be substituted by VC at this point. So VC, and this can be also written as VC if VC is equal to VD. Now if you see compare these two equations, the left hand side has become the same, VC minus VA, VC minus VA, and VC minus VB, VC minus VB. So because the left hand sides are same, that means the right hand side should also be same. So just you can say equating these two or dividing this by this, I will get R1 by R2, because left hand side is same for both equations. Therefore R1 by R2 should be equal to R3 by R4. So therefore in a Wheatstone bridge setup, Wheatstone bridge setup, if I know this relation will always be satisfied, R1 by R2 is equal to R3 by R4. And so if I don't know the resistance across any resistor, then I can one resistor and I know the other three, I can compute the resistance of that one of the resistor by knowing the other three resistance. Okay, next we will discuss Kirchhoff's law. Kirchhoff's laws are fundamental laws which will help us solve current electricity, which will help us solve some of the complicated circuits and find out what are the currents flowing through them. So let us first discuss the Kirchhoff's law, and probably in the next video I would show some how to apply those Kirchhoff's laws to solve some complicated circuit problems. So first law of Kirchhoff is the junction law, or Kirchhoff's first law is the junction law, which says that if I have a junction, many wires are coming towards the junction, some are carrying current towards it, some are away. Okay, so say I1, I2, I3, I4, I5. So Kirchhoff junction law says that the sum of all currents which is going in is equal to the current which is going out. So the current which are going in is I1 plus I3 plus I4. Sorry, I2 plus I3 plus I4. So I2 plus I3 plus I4 is the sum which is going in. So because there is no net charge which is accumulated in this junction, the sum of currents which are going in must be equal to the total current which is going out. So here the current which is going out is I1 plus I5. So this is Kirchhoff's first law, which is the junction law, and Kirchhoff's second law is the loop law. So suppose I have a loop, I have a circuit like this. Here I have a resistor, here I have a resistor, here I have a battery, Here I have battery, here again I have resistor, and suppose there are some currents which are flowing from externally like this. So suppose for a general case, let me assume that current I4 is flowing like this, and current I3 is flowing like this, and current I2 is flowing like this, and let me say current I1 is flowing like this. So if I apply, and this one is R4, this is R3, and say this is R1 resistance value, and this is EMF. Okay, and for, let us take a convention that whenever potential is going up, that is a positive, and potential which is going down is negative. So loop law says that in a closed loop, the algebraic sum of all the potential difference, so the important words are closed loop, and the sum of all potential difference. So in a closed loop, like this, for example, this is a closed loop, the sum of all the potential difference across this closed loop is 0. So in order to see what is potential difference can be positive or negative. So let us see that when we go across a closed loop, let us use the convention then that whenever potential goes up, that is a positive, and whenever potential goes down, that is negative. Okay, so I have assumed a current like this. Now in a closed loop, so this is a closed loop, so let me start from here. Okay, so now when I travel, current is flowing, I have assumed the direction of current from here to here. That means the current is always travel from a higher to lower potential, so potential is going down. When I travel, I will travel along this path. Okay, so I will go from here to here, and then finally come back to here, so that it becomes a closed loop. Now when I go from here to here, because current is flowing in this direction, I have assumed, and we know that current flows from higher potential to lower potential. So when I go from here to here, the potential drops. So as our convention, whenever the potential drops, it is negative. What is the potential? V is equal to Ri. So I3 R3 is the first potential drop, and because that is a drop, that is negative. Now I have reached here. Then I travel from here to here. When I travel from here to here, the potential here, this is a battery, so this is the negative terminal, this is the positive terminal. So when I travel from here to here, the potential increases by the amount which is the EMF of the battery. So our convention is whenever potential goes up, I will take it as positive. So plus E. Now when I am going from here to here, current is flowing in the opposite direction. That means that this is at a higher potential at this point, based on the assumption of my direction of current. That means potential is going up from when I am traveling from here to here. That means I have to take the sign as positive. So plus, now V is Ohm's law, the potential up will be V I1 R1. And finally, from when I travel from here to here back to my original starting point, current is flowing from this direction to this direction. We know that current flows from higher potential to lower potential. That means there is a potential drop. So there is a drop in potential. So I have to take this as negative. So minus, from V is equal to Ri, minus I4. And the loop law says, Kirchhoff's closed loop law says, that sum of all the potential difference is equal to 0. So this is the statement. The statement of Kirchhoff's first law will be the sum of all currents, or junction law is sum of all currents directed towards a point in a circuit is equal to sum of all the currents directed away from the circuit. So these are all the sum of all the currents which are directed towards the point, and this is the sum of all the currents which are directed away from the point, and they should be equal. This is the statement of the Kirchhoff's first law. Kirchhoff's second law says that in a closed loop, the sum of all or the algebraic sum, sometimes the algebraic sum of all the potential difference across all the elements in a closed loop in a circuit is 0. So with this let us stop now, and in the next video we will see some applications of Kirchhoff's laws and how they help us solving some complicated problems. So see you in the next video.